back to the next sessions. In the previous videos, we went through classifying a higher order linear ODEs as homogeneous, non-homogeneous, and then the coefficient as constant or variable. In this video, I'm going to take solving a higher order linear ODEs, but these ODEs are homogeneous and then they have a constant coefficient. So I've gone through representations of equation 1 where I said that if the coefficients ANs are not 0, then it is a constant coefficient. If the GT is also equal to 0, it is homogeneous. How do we solve these problems? We use what we call, so the solution technique is called the root solution. In other textbooks, it is called the auxiliary equations, and other textbooks have it as the characteristics equations. So whichever textbooks you have, all these solution names are the same. Right. So it has been proven that for linear higher order ODEs, the assumed solutions will be of an exponential growth or exponential function. And with the principle of superpositions, we can have a linear combinations of these solutions. We've gone through tests for solution, and to realize that if this is a solution for a differential equation, to test for it, what do? We differentiate it respect to the highest order in the differential equation, then we do what? We substitute. So this is all we are going to do. We differentiate and we substitute into the differential given. Now before you do that, the lambda here and the assumed solution, it is called the root, or someone will call it as the eigenvalues. That's if I'm looking at the matrix form, or it is called the zeros of a polynomial. Zeros of polynomial means you are looking for factors of which the polynomials get to 0. When you find this root, now this lambda can be real and distinct root, it can also be a repeated root, so real and repeated. This same lambda can also be a complex root. Real and distinct means that if I have two solutions, they are not the same. Repeated means that they are the same. And then complex implies lambda is equal to a plus or minus ib. When we find this root, they are where we write the final solutions. So in the case of real and distinct, the solution is such that you have it as the linear combinations of all the roots. So C2 exponential lambda 2 through to the end solution. If it's a repeated root, then my yt is a multiplicity of the t's. So lambda t, because they are the same, I have the second one as t, lambda t, plus c2 t square e lambda t through to the last n, t n minus 1 e to the power lambda t. So here it's assumed that I have t to the power 0. That is how you start the multiplicity. Now for the complex case, I have a solution of the form that where a is the real part of the complex and then b is the imaginary part. So this is how you write the solutions. There are cases where you can have combinations. So you can have lambda to be complex and then it is repeating. We'll take examples as that. In that case, the solution becomes, so assuming I have solutions, lambda 1, 2 are the same complex, and then lambda 3, 4 are also complex. It means I have the first part, C1 cos bt plus C2 sin bt. This is the first part. Plus the second part becomes EAT times the multiplicity t, C3 cos C4 sine, and so on and so forth. This is how the solution will be like. So let me take an example here. The first example, I'm looking at real and distinct roots, so I'll take a new sheet. If I want to solve a higher order y prime prime, you realize that this is a second order. It is not a first order, so I can't use that first order technique. It is homogeneous because the GT is 0. The coefficients are also constant. The coefficient here is 1. Coefficient here is 3. Here is negative 4. They are constant. And so I can go ahead and use the root solution. How do I do that? So first, I take my assumed solution, which says my y is equal to exponential that. Because it's of the second order, I differentiate it twice. So first derivative, I have that. Second derivative, I have that. Equation 1, equation 2, equation 3. So I substitute this into equation star, which is my differential equation. Let's do that. I have lambda squared that. This is my substitution. I can factorize out. So assume solution, you substitute, you differentiate at this point. Now let's do factorization. I can have e lambda t out. I have lambda square plus 3 lambda minus 4 is equal to 0. If I divide through by lambda at, I'll have just this part equal to 0. So dividing through by, let me write it here. If I divide through by the e lambda t, I'll end up getting this result. Now this is where I find my root, or the zeros of the polynomial. That is finding factors such that you are going to get the polynomial. And the factors here is lambda minus 1, lambda plus 4 equal to 0. This means lambda 1 is 1, lambda 2 is negative 4. I can classify this as, so classification, they are real numbers and they are distinct. Hence I can write my final solution as y is equal to y of t is equal to c1e 1t, so t, plus c2 exponential negative 4t. This is my final solution. And so this is how we solve for higher order with homogeneous constant coefficient. This example on real and distinct. In the next videos, I'll take examples on repeated and complex roots.